save the questions for when we move out into the hallway. That said, if you have a quick question or you just want to clarify some detail or something, feel free to do that. So our first speaker is Gabe Nespoli, and along with Alex Andrews and Frank Russo, their poster is called FeatureFinder, a powerful signal processing tool.
Okay, so I'm here less to talk about research that I've done and more to talk about a tool or software package we coded that makes research easier. When working in the Smart Lab, Alex and I were frequently presented with the same problem in dealing with physiological data, where you've got lots of files, lots of data, and you want to extract some kind of feature, say an average over a certain amount of time, from each separate file. And for each, so the first way we tried doing this was with the commercial software packages that came with the recording hardware. So you record GSR, EMG, and then within the thing you'd select the region, say I want the average, and it would spit out a text file or something. It's obviously really clunky, it takes a long time, and it's not as specific as you'd like it to be. So we moved to MATLAB. Anyone who here doesn't have any MATLAB experience? I see a number full of coders, so you're joking, right? So obviously it made things a lot easier. Everything was automatic. It did what we wanted to at the press of a button. The problem with it was that we found that as we moved between different experimental paradigms, it required a relatively big change in some of the code to shift to a different paradigm or shift to a different student's experiment. And additionally, we wanted to extract different features from someone else if it was a different organization files, et cetera, et cetera. So we tried to generalize this code and make it easier so that we could give it to a student who has no MATLAB experience, and they could just throw their files in, pick an average, and it would spit out an SPSS-ready text file at the end. On the flip side, we wanted to make it good for the coder, so that if you had a big complicated algorithm that you wanted to apply to each of your files, you could just slot that in, use FeatureFinder to organize your files, and save it. So, just as a bit of an overview, in the general research process, you've got something happening in nature and you collect some data from it. You do some kind of processing to the data and extract a feature of interest, and then you do some statistics, write the paper at the end. And here our result is that he's waving, so we figured something out. The realm of FeatureFinder really lands right here. We're not concerned with how you collect your data, and we're not concerned with how you do your stats. We're just helping out with data processing and feature extraction. So as I said, we wanted to make it easy to use so that someone with no coding experience can just jump in and use it. Customizable so that if you're a total coder, you don't have to use any of the simple stock scripts that we have. And then something we also want to do is this intuitive file organization, which basically lets you browse your files based on your experimental paradigm. So instead of having a big long list of all your files from different participants and conditions, you can sort of browse based on condition, etc. So really quickly, this is what it looks like. You can set up a profile, and we've got filtering, your feature extraction, and your browsing along the bottom. So stock right on the front, we've got high pass, low pass, and notch filters that sort of kind of geared towards EMG, because you've always got those kinds. And then we've got other filters, which we'll talk about a little bit later. Basically a drop down with the custom filters if you can code it whatever you want there. Features, you select your window ranges. So for this particular feature, we've got a target window and a baseline window. In this experiment, the action of interest happened right there. We wanted to take the average of the target and subtract off the average of the baseline to give us the difference of averages value, which is printed up there. We can scroll through to check for integrity of data if we want to exclude some trials. And then when you're ready to hit process, and it gives you something in tabular text. So like this basis, what have you. Customizing. All right, we're going to customize a feature in a minute and a half. So we open our feature template. We've got instructions for the non-coder as to how to do it. But basically, you've got your data and the two window ranges. And so you can do whatever you want with it. Here we go. So we're taking the target. So we're taking the target range, that window we selected, from the data, and we're finding the mean of that region, and same thing with the baseline. And we're slotting that into end feature as the subtraction of those two things. I can't think of something quickly that comes to mind, so why don't we do maths? I assume people can follow sort of what I'm doing here. So now we've got something that's finding the maximum instead of the difference of averages. We're going to call this target max. And then when I run FeatureFinder, darn. Okay, so we need to add some files. We'll do that real quick. So I've got consistently named files. I pick what's different between them and defines them all. So we had different participants, different conditions, and different trials that were included in the file name. It's labeled all those files as such. There's a lot of data there, so I'm going to wait a little bit because it's one little laptop. And down here in our feature dropdown, we've got target max. So as I say, for this audience, doing that customization is probably a little bit more appealing when you've got a huge volume to apply to all sorts of different. Make a little change to it, you only have to change the algorithm, and then FeatureFinder is doing all of the other stuff for you. One last thing I'll say is that everything I said about features also applies to filters. So you can make custom filters. You can export the filtered data, so you don't have to use the features part at all, and just use it as a big filtering tool to organize it for you, get your huge long algorithm filter and filter data. So there's FeatureFinder in 5 minutes, and we'll see you outside.
We're here to talk to you today about some of the features of Liquid Loops, which is our new software, and we've built some tools on top of Liquid Loops that, like the title says, can help you out in terms of not only composition but music analytics. So later on, Dave and Glenn are going to talk to you a bit more in detail about the framework that Liquid Loops is built upon, but we're going to refer to some terms that might not make sense until later on. So we received some data from our partner Naresh with Smart Lab on the perception of our 256 bar form structures, which are basically all of the 8th note divided structures of a bar, so 2 to the 8th possible patterns with just 8 notes. And Naresh did a study where users listened to all of them and ranked their perception in terms of how orderly each bar form sounds and how active or lively it sounds. And the results are in this plot. They were also divided into 4 types of families within the Weigl DNA music structure that we'll once again talk about more later. We took this data and we built a little widget calling the cognitive overlay into our software. And basically it allows you to take this rectangle and resize it and filter over this data. And it'll change the types of bar forms that are available for use. I'll show you in a few more slides. And it lets you organize them based on the order and activity data that Naresh gave us. And
Can you start the presentation so we can actually
oh,
see
sorry.
it?
Go to the slideshow.
Go to the top where it says slideshow.
See the very top.
Play your cards.
So
That's
all right. So yeah, there's the filtering going on here. We've got the bar form wheel, which Dave and Glenn are going to talk about. We've also got a third dimension here, which lets you size each bar form in terms of its frequency within our corpus of loops. So the larger ones represent bar form structures that appear most often in our corpus. And you get this visualization, and the ones that fall within the reticular region show up on the wheel over here. As you can see, the filters moving across. There's a different selection.
Yes, this generalized is basically to any two-dimensional data set. So here we've done genres, so that's techno versus electro. You can kind of see how they correlate, so yeah, when they're in a straight line more or less. This is funk and house where it's more scattered. And we've also done this with artists. So you can basically look at how different artists are going to, how they work together now.
These are our in-house musicians, not famous artists, but you can use basically any body of data that you have. And so next we're going to talk to you about our beat seeker feature, which is also built on top of this bar form wheel. And what it does is it colors the wheel based on the frequency of, here we have it divided by instruments, so the frequency of a bar form's use within an instrument, within our corpus. So as you can see, we've got different distributions for kicks and snares. And using this visualization and the cognitive overlay tool, you can have a sort of cognitive and statistically driven composition process, which I'll talk to you later outside of, at the poster or during Dave and Glenn's presentation. So what you end up with is cognitively informed beat. So if you have any questions, this is at the posters.
Just want to make one minor acknowledgement to Tristan Loria, who helped me in collecting the data.
You should just say that
You have
because
any-
it's in the room.
No.
Are you gonna play any sounds or?
Later on.
Yeah. Austin?
With
Okay.
Dave.
We'll give a live demo of this sort of scenario later on.
Perfect.
So basically, you're just constraining the beat space in ways that are cognitively and emotionally.
Alright, so I'm going to talk to you about the ability of audio features to predict ratings of tiredness and anxiety music. And so there's been quite a bit of support for audio features like tempo, mode, and timbre to affect both physiological and psychological experience of music. And a recent review by Gabe Nespoli and Lindstrom suggests that low-level features play a particularly important role in this experience. So mainly features like timbre, tempo, dynamics, and articulation. Now, most of the studies that have looked at the ability of these features to kind of predict emotional content have mainly looked either at categorizing these, so establishing whether a track is angry or not angry, for example, or classifying them along continuous dimensions of valence and arousal, so how pleasant versus unpleasant the track is, or how exciting or calming it is. And so, there's also, one of these studies in 2011 by Irola looked at the ability of these audio features to predict valence and arousal across different genres, and what he found was that features acted quite differently across different genres. So what we wanted to do was firstly to see whether these audio features can predict ratings of emotions that are more specific but still continuous. So in this case, we looked at tiredness and anxiety. And the reason we chose these features was because emotions was because they both kind of often get grouped as negative emotions, and they're quite similar in terms of their valence, but they're also quite different in terms of their arousal, and they're very different in terms of how they affect our behavior and our cognition. So, and if you think about them, they're not binary opposites, but at the same time they're quite mutually exclusive. So if you try and think of a piece of music that makes you feel both tired and anxious at the same time, I think you'll have quite a bit of difficulty. And so as a result, we got quite a good range of ratings because the pieces that we had that were rated high on anxiousness were also generally rated low on tiredness and vice versa. And the other thing we wanted to see was whether these features would predict these ratings in a similar way across different genres. So we took 40 tracks, and 20 of those were classical, 20 were soundtrack, with 10 tired and anxious pieces in each genre. And we used MIR Toolbox to extract 12 low and mid-level audio features from these tracks. And we then ran 3 sets of linear regressions with these audio features as predictors and ratings of tiredness and anxiety as the dependent variables. And we did this for all the tracks combined, and then we separated into just the soundtrack pieces and just the classical pieces. Then we brought in 12 new pieces, which were also half soundtrack and half classical, and equally divided between tired and anxious, and tested this model by calculating predictive scores based on these different models that we derived. And then we calculated different scores between predicted and actual ratings to kind of look at the accuracy of how well these models performed. So what we found was, much like in Aurola's 2011 study, features did act differently across different genres. So when we looked at all tracks combined, spread and brightness predicted tiredness, and RMS and rhythmic square and brightness predicted anxiousness. In soundtracks, spread and pulse clarity predicted tiredness, whereas rhythmic square and pulse clarity predicted anxiousness. And in classical music, rhythmic square, brightness, and tempo predicted tiredness, and rhythmic square and zero cross predicted anxiousness. Then looking at the different scores, we saw that for tired pieces, the combined model actually performed much better than the genre-specific models at predicting tiredness scores, whereas the true was opposite for anxiousness, so the genre-specific models were actually quite a bit more accurate than the combined model. And so there is some support for the fact that audio features can predict continuous and specific emotional ratings. And audio features do differ across genres in the way that they contribute to emotional expression. So when we're deriving these models, it's important to, at least in some cases, make them genre specific.
Okay, hi everyone. I'm Jessica, and my poster is entitled Predicting Crowdsourced Musical Tags from Brain Activity. And this is work conducted by myself and colleagues from Dartmouth College. This table is just to give you a sense of the data that we're working with. So we've collected hemodynamic brain activity while subjects listened to music from several different styles. And we also collected last FM tags of this music. And then our task is, can we predict the tags from the brain data? And these last FM tags are typically related to the genre or mood of the music, or they generally relate to kind of higher level human judgments of the music. So they allow us to probe these types of representations in the brain. I'd like to use this example to give you an overview of the process that we used. So imagine we have some target examples. So we have a brain tags pair. So this is some brain volume that was collected during a piece of music that was associated with these tags. And then we want to see how accurately can we predict the tags of the music from the brain data. So the first step is to use an anatomical mask to extract. In this case, we're looking at the superior temporal sulcus, which we've hypothesized to be important for this task. And then we feed the STS into a simple k-nearest inverse classifier, which has several examples of brains and their corresponding tags. The KNN classifier then looks for the K most similar STSs and inspects their corresponding tags to make predictions about the target brain. And the predictions are in the form of an ordered list. Then we use precision as a measure of the success of our prediction, where precision at n is defined as the number of true positives in the top n positions divided by n. So that's how my results are presented, they're precision values. Here are the results. Precision at n was evaluated for each subject, and for n equals 1, 5, and 10, and for k is 1 and 5, using leave one out cross-validation overruns. And we found that the precision values were above our random baseline, significantly better than a random baseline in all cases and all configurations. But overall, we found that a KNN with K equals 5 worked best overall, performing as well as 28% better than the random baseline. So to conclude, we've shown that these last tics, these kind of higher level human judgments of music can be predicted from hemodynamic brain activity in superior temporal cortex. This contributes to kind of our other work that allows us to conclude that kind of high-level information used to label and categorize music is represented in distributed population codes in superior temporal areas. And we suggest that a better understanding of the underlying neural representation of tags or of these human judgments can help to inform automatic media annotation systems. So if we have a better idea of how these things are related in the brain, perhaps they can help us in kind of MIR systems outside of neuroscience. That's it.
Okay, well, I'll just do a little bit of scrolling. I don't have to make it less. Yes. Thank you, mystery buttons. Okay, so this is what I'm going to be talking about. I think it started playing now. This might be more complicated than I thought. So, continuous ratings of emotion. In this case, I'm trying to model very roughly how different people rated their felt emotional intensity while listening to a piece of concert. So this is some examples of individual responses. As you can see, there's a lot of variation across them. And this is some musical features, some score-based, some audio-based, that we would like to find some relationship between them, if there is one. We're not sure that there is, but if there is, that would be good. It would be something to work with. So there are many ways of putting these together, but what I've decided to do is look at an adaptive system as opposed to making some kind of linear combination. Because as you can see, looking at this in this, linear combinations won't work so well. But even as is, we need to simplify it a lot. So if we just break it down to, as in this case, each line here across this is one response that's been reduced to when it is increasing or staying the same or decreasing in emotional intensity. Pretty straightforward. So we can see across a set of signals or listeners, there's these patches of redness and blueness where there's a certain amount of agreement and consistency across people. And here we have our set of experts or features that have similarly been reduced to have comparable rates of variation that should then line up fairly well and maybe explain what's happening here person by person. It's often hypothesized that different people respond differently because they're reacting to different parts of the music. You know, people have different ears, different experiences. They might be sensitive to the trumpet. They might care more about harmony. And there's research to support those claims. So this is trying to put that into application to see what's driving what when. And if we aggregate these all together, we see there's a lot of similarity between the variation in the set of experts and in the set of signals. So maybe performance won't be that bad. So I'm using online learning here, which can be adaptive. It's not optimally adaptive, but with what it basically does is it trains a bunch of weights. It classifies, it works with the features to give them various values, like, you know, let's say feature 2 is really important, but feature 3 isn't a good predictor, and it goes sequentially, time point by time point, to see whether or not those weights actually give us the right prediction when we aggregate them together. So, for example, for this person's response, we have some features that come out being relevant for creating, in this case, it's the best inline prediction. As you can see, there's a big difference between this and this, and mostly because this is over-predicting a lot more variation than we're seeing here. In order to get around the fact that this is suggesting that there's a lot of changes in how people are sensitive, if this is even a reasonable model, I also looked at what I'm calling retrospective prediction. So basically just shifting the weights back and point to see if it's actually capturing variation that's related to the piece, to the signal initially. And so this is what we get when we look at the retrospective optimal values for predicting these, and we end up getting something that looks a little bit closer here. But if we evaluate this overall, we can see that different features, so this, what I'd like to do is use this to characterize different listeners and being sensitive then to different things. And so this is just averaging per person what features are most relevant. And this, I use two different algorithms for the online classification. So ignore them across from each other. But as you can see, there's a lot of variation as we go across. So what's being picked up, or what moments of change
end up aligning with these features are very different from person to person. Correlating between these just to see if our two algorithms are actually choosing the same features for the same person is being important. The correlations are not too bad. Most of them are above 0.5, so that's a little encouraging despite all the gross breaking of the model that I've done to get to this point. But still, the performance at actually predicting when people are changing their responses of their felt emotional experience when they're reporting this ends up not being that well documented, even in these retrospective funny modelings that I do. So in the end, this is really just a beginning at looking at whether adaptive processes are perhaps advantageous for describing how people are responding, but regardless, the variation between subjects is pretty clear, even with this quasi-broken application. So if you have any questions about how all these colorful things come up, it's my question.
Yeah, so we do have one more. David and Weigl, Catherine Guastavino, and Daniel J. Lupton. The talk is called The Effect of Rhythmic Distortion on Melody Recognition.
So we'll start with one more. So I'm David, and I'll talk to you about our study on rhythmic distortion and melody recognition. First, a little bit of motivation for why we're pursuing this study. We're motivated by what's been called the multi-experiential challenge to MIR. So this was outlined by Stephen Giamou in the very early days of the field as the creation of rigorous and practical theories concerning the nature of experiential similarity and relevance. And it was identified then as one of the key research priorities for MIR, and it's been fairly underexplored since then. So in particular, I'm interested in this notion of topical relevance, which is a measure of how well a returned information object maps to the query that used it. And in doing this, we're looking at melodies as perceptual objects, perceptual information objects, made up of different facets, such as, for example, pitch and rhythm. And in the cognition literature, this idea of how different facets contribute to an information object has been explored through two different perspectives. One looks at how all these different facets merge together to make one whole, and this is sort of the Gestalt psychology, auditory scene analysis type approach. Another way to look at this is how, once we have this perceptual whole, how much can we mess about with the individual facets? How much can we distort them before it falls apart and loses its identity? So that's the approach we're taking here. Now, a number of previous studies have looked at this idea, generally using a methodology of melody recognition, where participants listen to a bunch of jumbled up melodies, distorted in various different ways, and try to recognize them and write them from the melody. Now, typically they look at pitch versus rhythm and their contributions to melody recognition. The distortions are usually things like an equitonal distortion producing a rhythm-only melody, or an isochronic distortion producing a pitch-only condition. And usually they find that pitch is far more important than rhythm when it comes to melody recognition. Now we feel that rhythm has been overlooked a little bit, has been shortchanged a little bit in these studies, because the stimuli that are typically used are highly familiar melodies such as Twinkle Twinkle Little Star, which often are very close to isochrony to begin with. So this rhythm distortion of imposing isochrony doesn't actually do that much necessarily. So that's one problem with the previous studies. The other is that they don't actually quantify the degree of distortion. So hoping to address these issues, we've released this study. We have the same sort of paradigm where people recognize melodies and write down the name, but we have slightly more complex rhythmic distortions. So we have this shuffled condition where every note duration in the melody is gathered and redistributed randomly among the notes. We have the randomized condition where you just roll a dice for each individual note and come up with a random value for each duration. And we have the stretched condition where you uniformly slow down the melody. And finally, we also have the isochronic condition as a we then apply a distance metric called the chromotonic distance to quantify the degree of distortion. I'll be happy to talk to you about that post. And indeed, we found that recognition rates were significantly lower in the randomized condition of the isochronic condition. So this supports our notion that the isochronic distortion alone isn't enough to nullify rhythm, and perhaps rhythm might be more contributing to melody recognition than previously assumed. So unfortunately, we didn't find a significant correlation of our distance measure with recognition rates, which was disappointing. However, we will try some other distance metrics. For example, this directed swap distance has performed better in previous research compared to Cuban values. So that's in the future. So very quickly, some outcomes of this stuff. So for music cognition, we've reassessed the contribution of rhythm to melody recognition and found it to be possibly more than previously assumed. We've applied a perceptual evaluation of rhythmic distance metrics in a melody recognition context. And in terms of MIR, we're working towards addressing this multi-experiential challenge. And in particular, we're looking at the notion of topic